Okay, so now we've got our solution to the Kalan-Samanzik equation. And what do we know? Well, we know that this term over here is the usual perturbative expansion, now expressed with the running coupling. And we know that this final factor over here that I've just outlined, this expresses how the amplitude of the two-point correlation changes because there's an anomalous dimension. So it expresses the non-trivial scaling of the field. So that second ring term is because you've got a non-trivial anomalous dimension, and the curly G term is because you have a running coupling. Now let's get to the puzzle. So I want to go back. How did we define the beta function? Well, the beta function was m dgp dm. So this blue box here that I've drawn, and I said sine. So let's return to that equation. So beta is equal to m dgp dm. And I can now express things in terms of the log of p over m. So this is equal to m d log p over m dm dgp d log p over m. And if you calculate this out just using the usual rules of calculus, you've got one derivative to evaluate, so that's no big deal. But this gives us minus dgp d log p over m. Now, the question that I was asked is about a sine. So if you look at this equation in the red box, we've got beta is equal to minus dgp d log p over m. And inside the green box, we've got beta is equal to dg bar d log p over m. So the question was, did we make some sign error? Well, no, we didn't. It's quite clear that g bar and gp are not the same objects, not the same thing. Okay, so you only run into a puzzle if you see that G bar and GP are the same thing, but still you may be feeling a little uneasy that the sign in the green box is what it is. So I'd like to explain why we get the sign that's shown in the green box. And where does that sign come from? Well, I hope you can see that this is nothing but solving the Kalan-Samanzik equation. So now let's solve the Kalan-Samanzik equation using a very nice model due to Coleman, and we'll see that that sign in the green box is absolutely correct. So let's just remove this. We don't need it now. Now you know what the puzzle is, what I was asked, and we'll solve that now. Good. Okay. So what's Coleman's model? Well, he's got a very nice physical model. So let me just tell you what it is. So here is Coleman's model, and this was invented just to help us to think about the Kalan-Samanzik equation. So Coleman's model goes like this. We have a pipe. So let's label this as a pipe. And in fact, there is bacteria in the pipe. Good. And what we will do to describe this problem, we will invent a density. So D, which can be a function of time and position. So this coordinate over here will be the x coordinate. So specifying x says where you are along the pipe. And d of t comma x is equal to the density of bacteria. So if you're at a certain position along the pipe at a certain time, there'll be a certain density, and that density will be the d of t comma x. The other thing that we will do is we will imagine that there's some exponential growth. This is pretty standard growth in epidemiology. So we will say that the change in the population of bacteria, so dt of x dt, is proportional to, so the change in the density of bacteria is proportional to the current density of bacteria. And that makes sense because it's your current population that's going to be reproducing to produce your future population. So that's pretty straightforward, just exponential growth. Now let's change this slightly. And the way that we'll change it, let's imagine that we introduce some flow. So let's imagine that the fluid in the pipe is flowing. So these blue arrows represent fluid flow and with a velocity v of x, so that the bacteria are actually being swept along the pipe. Then we have to change our dynamics. So this equation is no longer true when we have the fluid flow. When we have the fluid flow, the correct equation is d by dt. So we've still got the rate of change, but now we've got minus v of x d by dx. So I think this is called the convective derivative, something like that. It's a pretty standard thing in fluid dynamics. Then there's the minus rho of x acting on d of t comma x is equal to 0. And that's all that's changed. All that has changed is this term proportional to v. Okay, so to get some insight, let's try to solve the equation. Let's imagine, so what are we interested in? We are going to be interested in the bacteria inside this little red segment here. So inside that little red segment, we want to figure out what is the d of t comma x. So that's what we're trying to figure out. Now this fluid is flowing. So if I want to work out what is the density of bacteria in that little segment over there, where I should actually look, I should look upstream at a segment sitting over here. Because after some time, this green segment flows to where the red segment is. So to understand the red segment right now, I need to look at the green segment at some point in the past. And the green segment is where the red segment would have been. So that's how the model will go. Now, let me just explain. Maybe there's one thing in this model that I could make a little clearer. So let me do this now. Why do we have this growth rate which depends on x? So we're saying that the growth of the bacteria depends on where you are along the pipe. Well, maybe over here I've got a lamp and the lamp is shining onto the pipe and that's giving energy to the bacteria. So in this little portion of the pipe over here, the bacteria reproduce far faster than they do in places that are not illuminated by the lamp. So if we look at this equation, I think that, I hope that this equation in the bottom of the page, which I have just boxed now in blue, is clear. It's just the equation for the density of the bacteria. And the only idea that I've introduced now, so we're looking at this equation, trying to figure out how to solve it. The only idea that I've introduced now is if we are trying to find the bacteria inside this little red segment, then we need to look at the green segment in the past, because it's the green segment that flowed to where the red segment is. Okay, we'll continue in a moment.